Let's start now. Protostars. Every star in the universe begins the same way, as a cold, dark cloud of gas and dust floating silently through space. But when gravity begins to pull that material together, something extraordinary happens. The cloud collapses inward, heating up and forming a dense glowing core. This is called a protostar. A protostar is essentially a star in its infancy. Nuclear fusion hasn't started yet, but the object is already incredibly energetic. As gravity compresses the core, temperatures begin climbing toward the critical threshold of about 10 million degrees Celsius, the point where hydrogen fusion can finally ignite. During this phase, the forming star is chaotic and violent. Powerful jets of material shoot out from its poles at thousands of kilometers per second, while a swirling disk of gas and dust surrounds it. This disk is called a protoplanetary disk, and it's the birthplace of future planets, asteroids, and comets. Protostars can be enormous, sometimes 10 to 15 times larger than the star they will eventually become. Over time, they lose mass through powerful stellar winds and gradually shrink. This stage doesn't last very long on cosmic timescales. Massive stars may remain protostars for only about 100,000 years, while smaller stars can stay in this phase for up to 10 million years. But eventually, the core temperature becomes high enough for hydrogen atoms to begin fusing into helium, and when that happens, the true life of a star finally begins. Brown dwarfs. But not every collapsing cloud becomes a true star. Sometimes gravity almost succeeds, but not quite. These objects are called brown dwarfs, and they occupy a strange middle ground between planets and stars. They form in the same way as stars, from collapsing gas clouds, but they simply don't gather enough mass to ignite sustained hydrogen fusion in their cores. To become a true star, an object must reach about 80 times the mass of Jupiter. Brown dwarfs fall short of that limit. Most range between 13 and 80 Jupiter masses. Some brown dwarfs can briefly fuse deuterium, a heavier form of hydrogen, but this process is short-lived. Once that limited fuel runs out, the object slowly cools and fades over billions of years. Because they never achieve full fusion, brown dwarfs are dim and difficult to detect. They glow faintly in infrared light, invisible to the human eye. Their atmospheres can even contain molecules like methane and water vapor, similar to giant planets like Jupiter. In fact, if you looked closely, a brown dwarf might appear as a deep reddish or purplish object drifting quietly through space. They are often called failed stars, but in reality, they reveal something important about the universe. Gravity sometimes comes incredibly close to creating a star, but just misses. Red dwarfs. If brown dwarfs are almost stars, red dwarfs are the smallest stars that truly succeed. These tiny stars may not look impressive, but they are actually the most successful stars in the entire universe. In fact, roughly 75% of all stars are red dwarfs. They have masses between about 8% and 60% of our Sun's mass, just enough to ignite hydrogen fusion in their cores. But what makes red dwarfs remarkable is how slowly they burn their fuel. Our Sun will live for about 10 billion years. Red dwarfs, on the other hand, can live for trillions of years, hundreds of times longer. The reason is simple: they consume hydrogen incredibly slowly and mix their fuel efficiently throughout their interiors. And here's something fascinating. The universe itself is only about 13.8 billion years old. That means not a single red dwarf has ever reached the end of its life yet. Every red dwarf that has ever formed is still shining today. These stars glow with a deep red or orange light and have relatively cool surfaces between about 2,300 and 3,800 degrees Celsius. But despite their calm appearance, many red dwarfs produce powerful stellar flares that can blast nearby planets with radiation. Still, their extraordinary longevity means that long after stars like the Sun disappear, red dwarfs may be the last stars still shining in the distant future of the universe. Orange dwarfs. Slightly larger and brighter than red dwarfs are orange dwarfs, also known as K-type stars. These stars sit in a perfect middle ground between small, long-lived red dwarfs and hotter stars like our Sun. Their masses typically range from about 60 to 90% of the Sun's mass, and their surface temperatures fall between roughly 3,800 and 5,200 degrees Celsius. Because of their balance between stability and longevity, orange dwarfs are sometimes called Goldilocks stars. They are not too hot, not too unstable, and they can burn steadily for 15 to 30 billion years, much longer than Sun-like stars. This makes them extremely interesting for astronomers searching for habitable planets. A planet orbiting an orange dwarf could enjoy stable conditions for tens of billions of years, giving life far more time to evolve than it has had on Earth. Some scientists even believe that the best place to search for advanced extraterrestrial life might not be around stars like our Sun, but around quiet, stable orange dwarfs scattered throughout the galaxy. Yellow dwarfs, the class of stars that includes our own Sun. These stars have masses very close to one solar mass and surface temperatures between roughly 5,200 and 6,000 degrees Celsius. They shine with a bright yellow-white glow and generate enormous amounts of energy through hydrogen fusion in their cores. Our Sun, for example, produces about 380 trillion watts of power every second. Yellow dwarfs remain stable for around 10 billion years, which turns out to be an ideal timescale for complex life to evolve on surrounding planets. Earth formed about 4.5 billion years ago, meaning our Sun is roughly halfway through its life. But eventually even stars like the Sun run out of fuel. When that happens, their cores begin to contract while their outer layers expand dramatically. And that transformation leads to the next stage of stellar evolution. White stars. Some stars are hotter and more massive than yellow dwarfs. These are called white stars, also known as A-type stars. They can have masses between about 1.4 and 2.1 times the mass of the Sun, with surface temperatures ranging from roughly 7,500 to 10,000 degrees Celsius. Because they are hotter, they also shine much brighter. One famous example is Sirius A, the brightest star in Earth's night sky. But there's a trade-off. The more massive a star is, the faster it burns through its fuel. White stars may shine brilliantly, but they live relatively short lives, often only 1 to 3 billion years. That's far too short for complex life to develop on surrounding planets. In cosmic terms, these stars live fast and die young. Blue-white stars, these massive stars, classified as B-type stars, are far more powerful than the Sun. They can contain between 2 and 16 times the Sun's mass and reach surface temperatures of 10,000 to 30,000 degrees Celsius. Their intense radiation makes them tens of thousands of times brighter than the Sun. But that incredible brightness comes at a cost. Blue-white stars burn through their nuclear fuel extremely quickly, often living only 10 to 400 million years. They also produce powerful stellar winds that blast material into surrounding space at thousands of kilometers per second. These winds can shape nearby gas clouds and even trigger the formation of new stars. Eventually, many blue-white stars end their lives in spectacular explosions known as supernovae, blue giants. At the extreme end of the stellar spectrum are blue giants. These are among the most massive and luminous stars in existence. Some contain more than 90 times the mass of the Sun and reach surface temperatures above 50,000 degrees Celsius. Blue giants shine millions of times brighter than the Sun and dominate the regions of space where they form. But they are incredibly rare. Only a tiny fraction of stars in the galaxy belong to this class, and despite their immense power, they live very short lives, sometimes only 1 to 10 million years. Their intense radiation sculpts entire star-forming regions, ionizing surrounding gas and creating enormous glowing nebulae. In many ways, blue giants act as cosmic architects, shaping the structure of galaxies before their dramatic deaths. Red giants. Eventually, stars like our Sun run out of hydrogen in their cores. When this happens, the core contracts and heats up while the outer layers expand outward dramatically. the star transforms into a red giant. Red giants can swell to 10, 50, or even 100 times their original size. If the Sun becomes a red giant, which it will in about 5 billion years, it may expand far enough to engulf the inner planets of our solar system. Despite their enormous size, red giants actually have cooler surfaces, typically between 2,500 and 4,000 degrees Celsius. That cooler temperature gives them their distinctive reddish color. Inside the core, helium begins to fuse into heavier elements, continuing the star's evolution. But this phase does not last forever. Planetary nebulae. Eventually, many red giants reach a point where their outer layers become unstable. The star begins to shed its atmosphere into space, creating vast, expanding shells of glowing gas. These beautiful structures are called planetary nebulae. Despite the name, they have nothing to do with planets. Early astronomers simply thought they looked like faint planetary disks through small telescopes. Planetary nebulae can form stunning shapes: rings, bubbles, spirals, and complex clouds of colorful gas glowing in shades of blue, green, and red. This stage is incredibly brief in astronomical terms, lasting only 10 to 20,000 years. But during this time, the star releases huge amounts of enriched material into space: carbon, nitrogen, oxygen, and other elements that will eventually become part of new stars, planets, and perhaps even life. White dwarfs. At the center of a planetary nebula lies the remnant of the original star. This object is called a white dwarf. White dwarfs are the dense cores left behind after stars like the Sun shed their outer layers. They pack roughly the mass of the Sun into a sphere about the size of Earth. The result is mind-bending density. A single teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs no longer generate energy through fusion. Instead, they slowly cool and fade over trillions of years. They represent the final stage in the life of most stars in the universe. Blue supergiants. Some massive stars evolve into blue supergiants before reaching the end of their lives. These enormous stars can shine tens of thousands to millions of times brighter than the Sun. Their surfaces are extremely hot, and they lose mass rapidly through powerful stellar winds. Blue supergiants are unstable and short-lived, existing for only a few million years before collapsing or exploding. Red supergiants. These colossal stars can expand to more than 1,000 times the radius of the Sun. If one were placed at the center of our solar system, its surface could extend past the orbit of Jupiter. A famous example is Betelgeuse, the bright red star in the constellation Orion. Despite their enormous size, red supergiants are relatively cool on the surface, giving them their deep crimson glow. But deep inside their cores, they are forging heavy elements all the way up to iron. Once that process reaches its limit, the core collapses. And when it does, the result will be one of the most powerful events in the universe: a supernova. Wolf-Rayet Stars. Among the most violent stars known are the Wolf-Rayet Stars. These stellar monsters are incredibly hot, incredibly bright, and incredibly unstable. Unlike our Sun, which quietly burns hydrogen, Wolf-Rayet stars are nearing the end of their lives. They are so hot and energetic that their outer layers are being blasted away by powerful stellar winds traveling millions of kilometers per hour. These winds are so intense that they strip the star down to its core, revealing layers of helium, carbon, and oxygen normally hidden deep inside. Some of these stars shine hundreds of thousands of times brighter than the Sun. But that brilliance comes at a cost. Their lifespans are extremely short, often only a few million years, and when their lives finally end, they don't fade away quietly. Many explode as some of the most powerful supernovae in the universe. Hypergiants. If Wolf-Rayet stars are violent, hypergiants are simply enormous. Hypergiants are among the largest and most luminous stars ever discovered. Some are so large that if one replaced our Sun, its outer layers would stretch beyond the orbit of Jupiter. These stars burn their fuel at an incredible rate. Their cores are furnaces where heavier and heavier elements are forged: hydrogen into helium, helium into carbon, and eventually into even heavier atoms. But this furious burning makes hypergiants unstable. Their outer layers can expand, contract, and erupt with massive stellar outbursts. Some hypergiants even shed entire shells of gas into space, creating enormous glowing nebulae around them. And like many giant stars, their fate is sealed. They are destined to end in spectacular explosions. Supernovae. A supernova is one of the most powerful events in the universe. In a single moment, a star can release more energy than our sun will produce in its entire lifetime. For a brief time, the exploding star can outshine an entire galaxy. Supernovae happen when massive stars run out of nuclear fuel. Without the outward pressure of fusion to hold them up, gravity takes over. The core collapses in a fraction of a second, triggering a massive explosion that tears the star apart. These explosions are not just destructive, they are creative. Nearly all the heavy elements in the universe, including iron, gold, and uranium, were forged in supernova explosions. The atoms that make up planets, oceans, and even our own bodies were once scattered across space by dying stars. In a very real sense, we are made of supernova debris. Neutron stars. After a massive star explodes, its core may collapse into something extraordinary. A neutron star. Neutron stars are among the densest objects in the universe. Imagine compressing the mass of the Sun into a sphere only about 20 kilometers wide. The result is an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. Inside a neutron star, atoms can no longer exist normally. Electrons are crushed into protons, forming a sea of neutrons packed together with unimaginable pressure. Despite their small size, neutron stars often spin extremely fast, sometimes hundreds of times per second. But some neutron stars do something even stranger. Pulsars. A pulsar is a rapidly rotating neutron star that emits beams of radiation from its magnetic poles. As the star spins, these beams sweep across space like the beam of a lighthouse. If Earth happens to lie in the path of those beams, we detect them as incredibly precise pulses of radio waves, X-rays, or gamma rays. Some pulsars spin once every few seconds, others spin hundreds of times per second. The precision of these pulses is so remarkable that pulsars are sometimes compared to atomic clocks. In fact, scientists use them to test theories of gravity, measure cosmic distances, and even search for gravitational waves. But among neutron stars, there exists an even more extreme category. Magnetars. Magnetars are neutron stars with magnetic fields so powerful that they defy imagination. Their magnetic fields are trillions of times stronger than Earth's, the most powerful magnetic fields known anywhere in the universe. If a magnetar were halfway between the Earth and the Moon, its magnetic field could wipe the data from every credit card on the planet. But magnetars don't just sit quietly in space. Their intense magnetic stress can crack their crust, triggering massive starquakes. These starquakes release bursts of high-energy radiation powerful enough to be detected across the galaxy. In just a fraction of a second, a magnetar can release as much energy as our sun produces in hundreds of thousands of years. Black holes. Sometimes the collapse of a massive star goes even further. Instead of forming a neutron star, gravity compresses the core into a black hole, an object so dense that not even light can escape its gravity. Black holes are surrounded by an invisible boundary known as the event horizon. Once anything crosses that boundary, escape becomes impossible. Matter falling toward a black hole forms a spinning disk of superheated gas called an accretion disk. As this material spirals inward, it heats up to millions of degrees and releases enormous amounts of radiation. Some black holes even launch jets of particles that shoot across space for thousands of light years. Despite their terrifying reputation, black holes play a crucial role in shaping galaxies and the evolution of the universe. Binary stars. Not all stars live alone like our sun. In fact, many stars exist in pairs known as binary systems, where two stars orbit around a common center of gravity. These systems can produce some of the most dramatic interactions in the cosmos. If the stars are close enough, material from one star can be pulled onto the other. This process can create powerful bursts of energy, intense X-ray radiation, or even trigger stellar explosions. Binary systems are also responsible for some supernova events and the formation of exotic objects like neutron star pairs and black hole binaries. In many ways, binary stars turn stellar evolution into a cosmic dance. Cepheid variables. Some stars behave like cosmic heartbeat machines. Cepheid variable stars periodically expand and contract, causing their brightness to rise and fall in a predictable pattern. What makes them special is that the time it takes for a Cepheid to complete one cycle is directly related to its true brightness. Because of this relationship, astronomers use Cepheid variables as cosmic measuring tools. By comparing how bright they appear from Earth with how bright they truly are, scientists can calculate their distance with remarkable accuracy. These stars have helped astronomers measure the size of our galaxy and even determine the expansion rate of the universe. Carbon stars. Carbon stars are among the most visually striking stars in the night sky. These stars have atmospheres rich in carbon created through nuclear fusion deep inside their cores. As carbon rises to the surface, it reacts with other elements and forms dark molecules that absorb blue light. The result is a star that glows with a deep orange or red color, sometimes appearing almost ruby-like through telescopes. Carbon stars are also major contributors to the chemical enrichment of the universe, releasing carbon and dust into space that will later help form new stars, planets, and possibly life. Novae. Sometimes a star doesn't explode completely. It simply erupts. A nova occurs when a white dwarf star in a binary system pulls hydrogen gas from its companion star. As this gas builds up on the dwarf's surface, pressure and temperature rise until nuclear fusion suddenly ignites. The result is a powerful burst of light that can make the star appear thousands of times brighter for a short period. Unlike supernovae, however, the star survives the event. In many cases, the process repeats again and again over thousands of years. Population 3 stars. Long before our Sun was born, the universe contained a very different kind of star. Population 3 stars were the first generation of stars ever formed, appearing only a few hundred million years after the Big Bang. These stars were composed almost entirely of hydrogen and helium, the only elements that existed at the time. Without heavier elements to cool their gas clouds, these stars likely grew to enormous sizes, possibly hundreds of times more massive than the Sun. Their lives were short but transformative. When they exploded, they created the first heavy elements in the universe, paving the way for future stars, galaxies, and planets. To this day, astronomers have never directly observed a population 3 star, but their fingerprints are written throughout the cosmos. Black dwarfs. And finally, we reach a star that may not yet exist anywhere in the universe. Black dwarfs are the theoretical final stage of stellar evolution for stars like our Sun. After billions of years as a white dwarf, slowly cooling in space, the star would eventually lose all remaining heat and light. What remains would be a cold, dark, stellar corpse, a black dwarf. But the universe is not old enough for any black dwarfs to exist yet. The cooling process would take far longer than the current age of the cosmos. So for now, black dwarfs remain a prediction of physics, silent witnesses waiting in the distant future of the universe. The cosmos is filled with stars that are far stranger than the tiny points of light we see from Earth. If you enjoy exploring the strangest and most fascinating facts about the universe, make sure to subscribe to Paint Facts and join us for the next journey into the mysteries of space.